Okay, so this is the introductory slides under week 1 for the modeling and simulation class. Okay. And so what we're going to be doing here is we're going to be studying mathematical models to give us an aid in understanding the physical world. So I know at least one of you said that you were looking at physics. My philosophy, this is just kind of my own personal definition, but I basically consider physics applied math and engineering applied physics, because it's like, with the math, if you're a straight mathematician, a lot of mathematicians, all they care about is the equations and the math. But what physicists do is they take those mathematical equations and apply them to the real world to study the real world. And then what engineers do is they take what the physicists did and then use those equations to design and come up with ways to control the real world, or to like build a bridge or a building that's going to withstand earthquake or a hurricane and things like that. So what we're looking at is we're going to be looking at basically differential equations, which is why the prereq for this class is calculus. It's because you need to know a little bit about derivatives, differential equations, and then what we're basically going to do is be integrating. So we're going to have a differential equation which describes the physical system, and then to simulate it, what we're effectively going to be doing is to integrate those differential equations and come up with a numerical solution. So like in calculus class, you would do they spend a lot of time in calculus class coming up with the actual mathematical solution to an integral, right? So like if you integrate the cosine, you end up getting sine plus maybe a constant term or whatever. But here we're going to be using a computer to numerically come up with a simulation. And so that then, of course, allows us to build models or to build actual things. Like one of the first airplanes, the Boeing 777 jet, was designed completely on a computer. So they didn't do like any paper drawings or anything, but they did the entire airplane was was created and designed on the computer before they went out and actually built it. Okay, so just some ideas like that. So the software that we're going to be using for this class is what's considered a 4th generation software language. So in some degrees, but basically we will be doing programming in this class, but it's a lot different than if you've had a Visual Basic or a C++ kind of class. The bulk of the programming we're going to be doing in here is number one, it's mathematical. So we're be doing integration and that kind of stuff. Now we will deal a little bit with like for loops or possibly while loops later on, but we're looking at doing calculations, thousands if not millions of calculations. Okay, so it's like, yeah, you could do this with your calculator, but you would have to redo the exact same equation thousands and thousands or even millions of times using the same equation, but your data is changing every time. And so that's where these tools come along. Now there's 2 primary tools. One of them is called MATLAB, okay? And actually, technically, that should actually be all capitalized there in that slide, because MATLAB is a acronym, okay, for Matrix Laboratory. And this was a software package. It was actually created many years ago by some graduate students in the engineering field, and they went on to sell it. And so now it's a very common commercial piece of software. Okay. There is a student edition of it available that you could download and install on your home computer. But after you paid the price, and you of course have to verify that you're a student to get the student price. But you don't need that for this class. So I want to make sure everybody's clear on that. You do not need MATLAB to purchase MATLAB for this class. Okay. But so the MATLAB here is a commercial software, right? So it's that basically means that if you want to run it, you have to pay their licensing fee. Now there's also another program called Octave. Octave is an open source software that is about 95% compatible with MATLAB. So pretty much everything we're going to be doing this semester, you could actually just do in Octave. Okay. However, if you've already logged in and went to the start here, one of the things that you would have seen there under the start here folder is this setup for the OSC account. Okay. And so guess your screen's not updating. Let me top500.org, I believe. I haven't been to it for a while, but this to me is kind of an interesting website, because what it does is it tracks the 500 biggest, fastest computers in the world. And I see Japan has got the fastest computer again. For many years, they had the fastest computer in the world, and then United States got one that was bigger and faster again and stuff. But this is kind of a interesting website talking about the fastest computers. I'm talking, these computers are like entire buildings. They've got thousands and thousands and thousands of processors in them. And so when you create this account, we'll actually be logging into a supercomputer. It's probably not on this 500 list, maybe not quite that big, but MATLAB is a MATLAB and Octave. They're basically about the same, and you could get them to run on your own computer, but like I say, you don't really have to, because you can, I'm asking you to create this account with the Ohio supercomputer, and we'll be using that to do some of the calculations, or to do our simulations and stuff. You may, if you don't want to do that, you could maybe get the student edition of MATLAB, or just go for the Octave open source software. And I'll be doing a couple of videos on using Octave specifically, okay, and I'll be uploading those. And you'll be able to do virtually all the simulations that we're going to be asked to do in this class. You can certainly do in Octave, and you can run it on your Mac or your Windows PC, or if you're really into computers and you got a Linux PC or Raspberry Pi, if you know what that is, Octave will run on all of those. They even have a version of it for the cell phone. I installed it a few years ago on my older cell phone and didn't really find it real useful on a cell phone, but they actually do have a version for a cell phone even. But and again, it's open source, which means it's free, and it'll run on virtually any computer. Okay, and you can do pretty much all your simulations on that. The only thing is, I I'm kind of planning on doing a couple of specialty homework assignments that kind of require you to use the supercomputer and to see a little bit more about what that's all about. But other than that, Octave would be sufficient for every assignment that you'll be asked to do. All right. So, but let's talk about let's talk a little bit here about Supersonic Jets for just a minute. Okay. So I was had the opportunity while I was working on my graduate degree. My advisor did a lot of work for NASA Lewis, which I believe is now NASA Glenn up in Cleveland. And so my advisor, he did a lot of different stuff with them. And so I kind of got into some of that also. And one of the things that they were doing is they were trying to simulate a supersonic jet inlet. Okay, now a jet, I know you all understand what a jet airplane is, right? But when we talk about supersonic, supersonic means it's going faster than sound. And NASA has like a test inlet up there that's rated for 2.5 Mach. Mach 1 means the speed of sound. And so this inlet was designed for going 2.5 times the speed of sound. All right. Now the speed of sound is an interesting barrier. Before they ever broke the sound barrier with an airplane, there was a lot of people saying, hey, this can't even be done. All right. You can't break the speed of sound. So of course, other people were like, nah, we can do it. But it's kind of interesting that when that happens, okay, there tends to be a shock wave. And there's some people were able to capture some beautiful pictures, kind of like the one I'm showing you here on the screen now, of what happens when an airplane crosses that sound barrier, and there's a lot of moisture in the air around the airplane, and you can kind of see these drastic shock waves. So you see like this picture. Now, what's interesting about this picture though is if you look right behind the cockpit, you see that little bit of moisture behind the cockpit. So that's kind of like another shock wave right there that's also occurring. Okay. Now, when an airplane breaks that speed barrier, or that Mach 1 speed barrier, and starts going faster than the speed of sound, okay, then you get into a problem. You got to make sure, right, these airplanes need a lot of oxygen, right? They burn oxygen out of the air. They use the oxygen to mix with the fuel and burn it to get that speed. And so obviously these things are going to need a lot of oxygen. But what happens though is, as you see like this, this missed shock wave here, where you end up getting the shock wave inside of the engine also. And the thing is that a jet engine is made up of like a bunch of fan blades. And if that shock wave was to hit those blades, it's going to cause a lot of turbulence and probably damage to those. All right. So I'm sure you probably at one time or another have seen a picture of the SR-71 black bird here. This is an amazing plane. One of the things that really amazes me is the technology of it, because it was like built in the late 60s. Okay, so I mean, this plane has been around for a very long time, about as long as I have, I guess. But it's technology. Some of the technology in this plane is just amazing, and some of it's probably still classified even. But when you see these cones on the jet engines here, these cones can actually move in and out to change how much air is getting into the engine based on the speed of the jet, and if they're trying to speed up or slow down and they need more oxygen or they want less oxygen. they can actually move that. So here's kind of a capture of this. So when you see this cone, you see that it's actually got a shape where it goes out, and it's really narrow down here around number 66. It's very, very narrow there. But then as we go beyond that, it spreads back out. And you see these little jagged lines here. Those actually indicate like where the shock wave could be at a given time. All right. And so when you have a supersonic jet, like I say, it needs a ton of oxygen to keep it, especially when it's, going faster than the speed of sound. It's going to be needing a lot of oxygen into that. And so the inlet is basically the area where it's allowing air in right before the fan blades of the jet engine. Okay, and if it doesn't have enough oxygen, then it's going to go into a stall condition. Okay, with airplanes, you can have kind of two stall conditions. You could have the one stall condition is when the wings lose lift and the plane starts just dropping. The other is when the engine itself stalls out. And that's what we're talking about here. If the engine is going to stall out because it's not getting enough oxygen. Okay. So this, go back to this simulation here. So this is a simulation of the test inlet that they had up at NASA. And when you look at this, okay, you see up here at the top is kind of a model of the throat of that inlet. So you see over to the left here, along the left side, is the inlet, that's where the oxygen is going to come into this engine. Okay, and so this whole thing we're looking at is just the inlet. So the fan blades are over here at the right hand side. Okay, so the fan blades are on the right hand side. And what we've got to get enough oxygen in this thing to have it run. But what's interesting is if for this thing to like run at optimal performance, okay, then you want there's a shock wave inside here, and the shock wave is over here at 23.1. Now these numbers here are actually divisions for the simulation. So what we did was we broke the area of this up, and the one thing I did not do on this, which I'm going to have to redo it because it doesn't have the units. But so this inlet is maybe 10 inches long or something. I don't even remember off the top of my head. But so we're breaking it up into little nodes, and we're calculating what is the pressure and what is the speed of the air moving through this inlet at each one of these nodes. So right now I've got like 40 nodes here, and I'm calculating that air. And so up at the top here, I'm plotting, and it's a different color depending on what the pressure is. So over here at the left, and this like deep blue is the speed is 2.5 Mach. And then we go into the neck here where it's really thin, and it slows down, and then it speeds back up some. And then here where that red line is, you see the red line, I'm running the mouse along right here. That red line indicates the shock wave. And so you can see here, if you look at this line in the graph down here, this blue line is the Mach number. So the Mach number, this thing's running at 2.5 or just under 2.5 Mach coming in. So the air, this is the movement of the air, how fast the air is moving in here. So the air is moving really, really fast along here, and then it's getting compressed because there's not as much room, because the neck, it's getting narrower and narrower, so it's getting compressed there, and the air is slowing down. And so you see it's slowing down here where it's turning red. It's getting close to Mach 1. And then it actually speeds back up, but then boom, here's the shock wave. It goes from up here almost Mach 2 and drops down to about almost half a Mach. Okay, so it's dropping about 1.5 Mach in just a very short area. And that's where the shock wave is inside of this engine. And so what you see is you simulate this, okay? You can see I'm changing the pressure. The pressure value up here in the top right is the pressure going to the fan blades, okay? So if I want to speed up the engine, I need to feed it some more air. So I need to increase the pressure into the fan blade. And so as you run through this simulation, you'll see as it goes along, it increases the pressure, okay? And so as you can see that, you can watch, if you watch this bottom graph, especially when it changes values here, you can see this kind of ripple coming on. And that ripple, okay, is that change in the pressure and the change in the amount of energy inside of here. And you can actually see these ripples up in the top with the colors. You can actually see those ripples through there. And those are kind of like little minor shock waves, and those can cause vibrations in the airplane. And it, you know, because they're vibrations inside the motor, inside the jet engine of the airplane. But what we're doing here is we're simulating this, okay? And it's basically a differential equation. So we're basically changing the pressure and integrating it and calculating what the new pressure is, what the new energy value is throughout this, what the mass flow is. You see the mass flow doesn't change a whole lot. Okay, but you can see the Mach number changes drastically, and the energy is changing drastically. So you're not going to be asked to do this particular simulation. Okay, this one's actually a little more complex because not only are we simulating in time, but we're also simulating position. Okay. So, but let me just kind of show you, if as the shock wave, as you increase the pressure, the shock wave moves up to the throat. Move it back a hair here. So as the pressure increases, you get into here to about the narrowest part of the throat. So see, like right along here, this entire way is the narrowest part. Now, if this shock wave gets over to the left where it starts expanding back out, okay, what happens is you're not getting enough oxygen into the engine and it'll go into stall. So if we slip over to the end of this, I sent you the link there. The link's posted. You can kind of watch this on your own time if you want to sit here and watch the whole thing. But as this shock wave moves over here to the left of the inlet, what's going to happen is it's going to blow out the front. So all this pressure build up in the back here is going to push the shock wave total outside of the engine. And you can see it down here. You can see it starting to just bounce around a lot. Okay, and that shock wave is pushing out, and it's going to fly out the front of the engine, and the engine's not going to have any oxygen, and so the engine is now at this point going into stall, and at this point my simulation even basically right goes. All right, but that's just kind of an example of what we can do with this type of simulation. All right, so hopefully that kind of gives you a little more of a feel for what it is that we're going to be simulating, and hopefully you find this kind of interesting. Okay. All right. So does anybody have any comments or any questions or anything there? You can put it in the chat window. All right, so just to kind of start off here, we're, the first couple of weeks here, we're basically just going to be working with the software. And in a lot of ways, this software, whether it's Octave or um, the MATLAB software, either way, it's basically kind of like a really advanced calculator. Okay, and so we just kind of need to learn some of the fundamentals of it so that we can do that. So let me grab the next set of slides. Okay, and I have lots of other videos and other information there. Okay, but let's just kind of go through the slides here for a little bit, and then I'll pop into Octave and show you those. And right now I'm waiting. You have to you have to do that registration with the OSC and get your account with OSC. And then once you do that, I have to ask them to give you access to MATLAB. Okay, because I don't think they're doing it automatically. I have to do a special request. So please, if you haven't already set up your OSC account, please go ahead and do that. And then here in a couple of days, I'm going to go in and I'll send the names of everybody who's created their accounts. And I'll ask the OSC to give you the MATLAB access. So I'm actually just going to show you Octave today. Okay. But before we get into actually trying to use it, I just want to talk about some of the various features, I guess, of it. All right. So it's a calculator in a lot of ways. It's more than just a calculator, but it's kind of a calculator, so it has variables. And one of the nice things about Octave or MATLAB over an ordinary calculator is the fact that we can name those variables. Okay, so we can create variable names and then we can reference those variables after the fact. All right, now they give us a few variables by default. So for instance, we know like pi is 3.14159, whatever. Okay, if you go to Octave, okay, or if you have MATLAB up and running, you could go to MATLAB either. But like I said, I'm going to do the information on how to get to MATLAB on the OSC computer a little bit later because you don't have your account set up for that yet. But did it start here? I think because I'm recording this, my computer's running very slow. It really, every time I try to do videos like this, it really tends to slow down and my computer runs a little. Yeah, so there, now I've got two of them open. All right, so this is kind of the interface for Octave, and the interface for MATLAB looks very, very similar, which we'll see. Okay, so, but this window right here is called the command window, and this is where we enter in commands. Okay, now later on, I'm going to talk about creating what's called an M file, which is a program file. So really, you don't want to work in the command window. What you want to do is create a M script or an M file. And that M file, the M actually comes from MATLAB, right? It's kind of MATLAB's extension. So it has a .m extension. And it's a text file full of commands, and then we'll execute that file. So instead of sitting here and trying to type 20 or 30 or 40 or 50 or 100 commands, we want to put them in a file, and then you just run that file, and it'll run them all. And so then if you need to do it again and make a slight change and rerun it, you just make that change to the file and re-execute it. All right, but this is the command window. And over here, this is just your directory, whatever directory you're in. And then the workspace this is going to list your variables and what kind of variables they are. So like right now, if I wanted to, I could create a variable x, and I could say, well, x is equal to 5. And so then over here, it just shows you, well, now you've got a variable. It's of class double, which means double precision. It's a very high precision variable, and it's just a scalar. It's a 1 by 1, which means it's a scalar. On the other hand, I could create a variable. A lot of times I create like a variable t for time, that because we're going to be, most of our simulations are going to be timed based. So we'll create a time variable. And so what I can do here is I'm going to say t equals 0, 1, colon 10. So this is going to create a variable with 11 values. All right, so notice this now. It number one, you see it didn't print anything out because I put that semicolon. So one of the great things about MATLAB and Octave is if you want to rerun a command, hit the up arrow key. So if you hit the up arrow key, you can scroll through your previous commands. So if I come up here, if I run this command, but I run it without the semicolon, you can see it prints out all of the different values. So what I've done is I've created a vector. This vector has 11 values. Why is it 11 values? Because it started at 0, right? So when you start counting at 0 and then you go to 10, that's 11 unique values. Okay. So then we could take something like, now I can create a variable x, and I'm going to say, well, x is t squared. And so I'm going to square it. So what I do here is now it took every value of t and squared it. Now notice here I used this dot and then the caret. The caret means power. Okay, so I'm, to the second power or squared. But because I wanted to do it on every individual element within here, I had to put that period there. It's a special notation to say do square each individual one. Okay, and so most of the time when we do these kind of things, we'll have to do that. But see, if you wanted to do this with a calculator, what would you do? Well, you would have to say, okay, well, x is equal to 0 times 0. And then you would say, okay, well, that then when you do the next calculation, you're going to have to say, well, that's 1 times 1. And then when you do 2 times 2, x is equal to 2 times 2. And then x is equal to, 3 times 3. And then x is equal to 4 times 4. And you would be doing it every single one of these calculations one at a time, and you have to do it over and over again. But see, that's the beauty of this software, is with this software, you have all the different values of t in there. And so when you come up with the x, now notice here, when I just type x and I hit the up arrow key, it'll just scroll through the commands that started with an x. But so see, now when I do the x equals t, t dot caret 2, it squared all of those. So that one command squared 11 different values and gave me the results of all 11 different values. Okay. Now I could have just as easily had 100 values. So when we look at like t, usually t is going to start at 0, but I could start it at like a minus value. So I could say, let's go from minus 10 and then step by 1 and then go to 10. Okay. And so if I don't put the 0 there, you see it just, I get all of that, or excuse me, the semicolon. But if I put the semicolon, it just doesn't show it to me. Okay, but now when I square those, now it's squaring 21 values in the blink of an eye. Okay, instead of you sitting there trying to go with a calculator and do something like, well, x is equal to minus 10 times minus 10, which is a square, right? And then I get 100, positive 100. Okay. If I wanted to do another variable, let's call it x3 is equal to t cubed. Okay. And I got this error message because I forgot to put my dot in there. Okay, so now you can see I've got t cubed. So we got t cubed here is minus 1,000 to plus 1,000. Okay. And so actually I think what I'm going to do is I'm going to redo that, but I'm going to go ahead and divide it by 10, so it's on scale with x, with the x. So x is going, and anytime you want to view a variable, you can just type in that variable name. So there's x. And I apparently redefined it there. So there's x, and here's x3. Okay, and so those are the values. So now one of the great things about this software is I can plot that. So I can plot t comma x, and then I'm going to make that blue, and then I'm going to plot t comma x cubed, which I labeled x3, and I'm going to make that red. Okay, and then I can plot that, and it'll pop up a graph. Okay, like I say, the one thing I've noticed with Octave on Windows computers especially is the first time you do a figure, it takes a little while for it to come up. Okay, but there you can see is my plot. Okay, and I've got x squared and x cubed there. Now we can actually label those, so we can label the x label is time, and normally we need to know what the units are. At this thing, I'll just call it seconds, and then I can do the y label, which is the magnitude. Okay, and it might have units of volts or something, whatever the units might be. All right, so when we look at our graph, then you can see the label. Okay, and you can put a title. Okay. And you can actually do a legend. Okay, with the legend, you can just say like x squared and x cubed, and you just have to do it in order because it knows how you plotted them, and then it'll put that legend in there. So here's we've got the title up here, and we've got the legend. Oops. Sorry. All right, so so we got the legend up there. We got a title. We've got x-axis, y-axis on there, and we can plot that. Now, one thing I wanted to kind of point out to you on this plot, though, is if we zoom in a little bit on it, you see it's not very smooth. You see how it's kind of pointed here? All right. So the reason for that is because we only have 21 values. Okay. So if I recall my t, here, and I'm going to go from minus 10 to plus 10, but instead of stepping by 1, which is what I did before, I'm going to step by 0.1. So now instead of having 21 values, I've got 201 values. And you see how it just printed out all those numbers? Okay, that's why when you do this, you really want to put the semicolon, because we don't want to look at all those raw numbers. They just, there's just turns to be too many of them. So if you get 200 or 2,000 of them, it's just too many numbers for us to deal with. And that's where the plots come in. So I've redefined t. So now I need to redefine my x. All right, so there's my x. And again, if I don't do it with the semicolon, I get 201 numbers displayed on the screen. But if I recall it, if I put a semicolon at the end of it, it creates it and it puts 201 there. So you see up here in this workspace, we can see that t is 1 by 201 elements. X is 1 by 201 elements. But we haven't redefined x3, so it is still only 21 elements. So what happens here, if I go to my plot, remember, if I just type P and hit the up arrow, I can recall the plot command to tell it to update the plot with the new values. But when I do this, I'm going to get an error message because T has 201 elements, but x3 only has 21. And so it won't let me plot those two. It'll plot t versus x2, but then it gives me an error message because x3 and t are different lengths. So if you see this error message, it's because your lengths don't match. And a lot of times they might only be off by 1. Okay, so you might have here we have 201, but your other value may only be 200. Okay. So you need to just make sure that the length of the vectors are the same when you're plotting them. Okay. All right, so I have to redefine my x3, so I'm going to press x3 and hit the up arrow key, and I'm going to recall that instruction, the cubed x3. Now I can hit P and up arrow and plot, and now you get that plot. And you can see that they're much smoother. Okay, so you can see these lines here along here are much smoother than they were when I only had 21 points. All right, so basically it depends on how fast your graph is changing, but a good rule of thumb is that when you're going to be doing a plot, you probably got to have at least 100 points at a minimum if it's curving at all. And if it's curving very fast, you may have to have 200 or 2,000. If you try to plot with too many, see, if I come over here and let's say that I take my t and I'm going to make it 0.001. So now notice that t is now 20,001. Okay. So then if I calculate my x, 3, and just my x, I'll do x equal to recall that one, right? So these are all now 20,000. So now if I try to plot this, I'm going to be plotting 20,000 points for the first graph, for the blue one, and another 20,000 points for the red one. And honestly, that's just way too much most of the time. Okay, because you can't see that difference because the resolution of your screen, if you think about a standard computer screen nowadays, it's high definition, which means that in the horizontal direction there's 2,000 points, and in the vertical direction there's 1,000 points if you're at a standard high def screen, which is the screen that I'm actually running this on right now. So it's 2,000 points left to right and 1,000 points top to bottom. And so if I'm plotting 20,000 points, I'm plotting more than I can really see here. All right. Now, if you're doing a plot and you're going to make it a really big plot that maybe you're going to print out on a very high quality printer and make it very big, like a poster size to put on the wall, then you may need 20,000 points or more. But for this class, probably anything more than 2,000 for a single line is probably overkill. All right, but hopefully you can kind of see here that what we're doing is, these are just standard, typical mathematical calculations, but we're executing this calculation. Like right now here, when I executed this command, I punched in this t cubed divided by 10, and I executed this command 20,001 times. Okay, so if you were trying to do that with a calculator, you would be there all day trying to, you do the first one and you do the second and the third, and you would be punching in numbers all day long. But this software will do those calculations for you in seconds or microseconds even. Okay, and so that is the beauty of this. So when we're doing simulations, we can do literally millions of calculations in just a very short time, especially if we're using one of those supercomputers that have thousands of processors. So, I was showing you this video here of this simulation. There was another grad student who was she basically did her thesis on this simulation, or on this jet inlet, not this simulation, but on the jet inlet. And so she was doing these sorts of simulations back in, this was, date myself here, but this was back in like 1998. She was doing this on, I think it was like a Pentium class computer. And to do this simulation, she would start the simulation on Friday afternoon at 4 o'clock and let the computer run all weekend long and hope that when she came back in on Monday, it was done. Okay, so it literally took all weekend to do a simulation kind of like this one that I have right here. This simulation here I ran using Octave. I created this simulation using Octave on my workstation at home. And my workstation at home has 2 Xeon processors, so it essentially has 12 processors in it, because each Xeon processor has 6 cores. And so it's got like 12 processors in it. And so I ran this, and it took about 6 hours on that computer to run. Okay, so when you're doing these sorts of simulations, depending on exactly how intense they are and everything, they can take days to run. And so that's where, like, the idea of using these supercomputers, like that supercomputer cluster at OSC, we can run a simulation that on your personal computer could take an hour, or could take 10 hours, or even it's several days, and it can be done in 5 or 10 minutes on the supercomputer. Okay. The only catch there is when you're trying to use multiple cores like that, you have to be careful, because you have to do a little bit of extra programming to make sure that it spreads the calculations over multiple cores. Okay, and so if you don't do those special modifications, you might not be gaining very much by using a great big supercomputer, because it's actually only doing the calculation on one processor anyhow. All right, but one of the nice things about MATLAB is it does a lot of that work for you. So when you run your simulation on MATLAB, it does at least not all the underlying programming that you could do to speed it up, but at least does some of it automatically. All right, so hopefully this gives you an idea of what we're going to be doing. Like I say, we're going to be simulating dynamic systems. And so I've got a few what I think are very exciting kind of simulations that we can do to get some very interesting graphs, okay, and things. So as we go along, we'll be doing a lot of different simulations. But here this week and next week, we're going to spend most of the homework assignments are focused on just getting you using the software. So like I say, you can use this Octave software. Okay, so you can log in and use Octave, or I mean, you can download and install Octave, or you can run the MATLAB. So I'll be contacting the OSC and asking them to give you MATLAB access through there, and I'll do a video on exactly how you get into and run the MATLAB software. But like I say, basically the screen looks pretty much like this. It looks a little bit fancier because it is commercial software, but it looks very, very similar to this screen here when you first start out. Okay. All right, one other thing, if you don't actually want to install Octave, but you want to kind of get started on your homeworks, you can go to a website called octave-online.net. And this is a version of Octave that is available just through your web browser, so you don't even have to install it. Okay, and so you can come in here and do just like I did before. I can create my t vector minus 10.1 to 10. Okay, and put my semicolon there again. If you don't put your semicolon, this is what you get, all these numbers. So that's the big point of the semicolon. It really helps. All right, and then once you do that, you can go in and you can say it's things like, well, x is equal to t dot caret squared. And then you can say like x3 is equal to t dot cubed divided by 100. Or excuse me, I think I divided it by 10. And then you can plot t comma x and t comma x3. Okay, and you can do a lot of your homework and stuff right here. I don't know, I've never put a label on these. See what that does. Yeah, so it redraws the graph, but with the label. Okay. One thing you can kind of do is you can use semicolons, and you can do like multiple of these on the same line. Or you can actually do them in a text file and create and use these scripts. Okay. So so you can just do this online without installing Octave. Okay. If you don't want to, like I say here, and I'll be doing a video on how to get into MATLAB on the OSC site here. Probably tomorrow I'll do that video. I've got another class today, so I won't be able to do it today, but I'll try to get it done sometime tomorrow and put the link there in Blackboard. Okay. All right, so anytime you're working on this, make sure you, if you run into any questions or anything, shoot me an email. If you're working on, you know, these MATLAB or Octave commands and you're getting an error message or whatever, please copy the command and the error message and send it to me. Send me as much information as possible so that I can hopefully see what the problem is right away and answer it. If you don't send me enough information, if all you do is send me the error message, I probably can't really tell what's causing the error message. So I need to see everything that you're doing. And that'll help me be able to guide you and point out where your issue might be. Okay. All right. Well, thanks for logging in today. And like I say, if you have any questions, give me a call. And that's about it.